So, thank you for your kind introduction, and thanks a lot for the invitation to speak to all of you here today, to be given this chance. I'm very happy to be here. And in the last lectures and also yesterday, volcanoes and volcanological processes have been covered the one or the other time. Let's look back to what we know or what we think to know, actually. We mentioned, or it was mentioned a couple of times already, that we actually don't know much if we go back, and the further we go back, the less we know. So what do we think to know? What, if you think back of how the early Earth would have been envisaged by, well, 5 years ago, 10 years ago, 20 years ago, you literally have everything, starting from warm little ponds. We saw that they're being back in fashion by the talk of Dimitar, and I'm a big fan of these as well, as you will see in a moment, even though I would frame them a little bit different. Then we had hell-like planets, we had ocean worlds, we had death ice bodies, we had literally everything. So what is true? We don't know. All of this is based on theories on, the only thing we have from the Hadean time are a few tiny crystals. So in a way, we are behaving as planetary scientists. I always was jealous of this ability to make great stories and great science out of a few data points. It's something we're not often allowed to do on Earth, but you have to do if you go to planetary sciences. So one of the big debates is whether we had a diversified surface or whether we had the monotonous ones. I want to take this picture here where you see now we had either just, not sure how to point, okay, we had just ocean floor and covered by water, the water worlds, or we had a bit more diversified structure. Don't take the image as it is, take the components. So we had some crust, we had orcs, we had oceans, we have diversity, and I think that is the key what we need. We can discuss about the abundance and about the structure, and actually we have to do, and probably we will do for the next 5, 10, 15, 20 years. So what are the key conditions for early Earth to function towards emergence of life? We need coexistence of gas, liquid, and solids in a form of, ideally, atmospheres, of oceans, of some compositions, and of geomaterials. And that's not the end. What we need are driving forces. We need the sun, we need gradients, chemical gradients, thermal gradients. Life in itself cannot grow only by water. We need to have the nutrients, we need to have some components enriching them to kickstart that. That goes back to the so-called habitable trinity model. I think you're all aware of that. Does this tell us where we find life, where life originated? No, not really. It can guide us to some environments, to some places where it might have been a little bit more likely than others. And I will now show you how actually volcanic processes and volcanology can even help you to foster and improve these environments. So to do this, we have to, first of all, remind ourselves, how do volcanoes work? I'm sure all of you have some basic understanding and knowledge about that. Still, I decided to put in the definition I found at the Encyclopedia of Britannica. So, volcanism, we have various processes, various phenomena. Surfacial discharge of molten rock, lava, magma, fragments, ash, bombs, pyroclasts. Now, next things might be a bit more surprising, hot water and steam. So the true driving force for volcanism is water. That might not be the first imagination everyone has, but it's the volatiles, the fluids dissolved in the magma, which drive volcanism. And even afterwards, if the magma is at the surface, we have strong interactions in terms of fumaroles, geysers, hydrothermal systems, where we have an intimate link of volcanism and hydrothermal system and water. Now you see from the title that I say today, well, volcanism today and in the early Earth work differently. Today, volcanism is intimately linked to plate tectonics. Plate tectonics exists for a long period, but not in the Archean and not in the Hadean, not in the way we know it as today. This is the image you also find at the Encyclopedia of Britannica. So you see we have the subduction zones, and you see some cycles where we are upcycling mantle material, and the volcanoes bring this upward. This stable plate tectonics is one of the key driving forces today. How did it work in the early Earth? So in early Earth, we consider that we had something which is called vertical tectonics. The plates weren't rigid enough to sustain long-term subduction. So what we had is something, you see here, some kind of circular structures. In the middle, we have ridges, troughs, trends, all of that. We have microplates. They move outward, and then they are recycled. How does that allow continental crusts, something on the surface, to form? Well, it does. You even can have, so these kind of subduction cells, we now have two here, they can actually interact. They can collide and form something which is called protocontinents. The amount of such continents might have been really small. That's okay. The key thing is they probably existed. So we have something which we can consider as landmass and all the elements involving in that. So these plumes I was talking of, they are considered to reach deeper than today plume cycle. So this is an older publication, now 10 years ago, where you see that they might cycle quite deep down to maybe even something core-like structure, so it didn't have a separation of the mantle yet, and they bring upward material from the middle and lower mantle and erupt it at the surface. So we have one really key mechanism to steer up the Earth and bring up metals, transitional metals, volatiles, and bring back to the surface and erupt there in form of lava flows, in form of gases, of ash, underwater and on land. So how do we know this? This goes back to some chemical links. If you look at the isotopes of some of the Hadean zircons, this is coming from this period. So to sum this up, we think we had this vertical tectonics at the early state of the Earth. Now we have this kind of stable subduction zone, and we had a transition in between. So yes, ever since we had a solid enough crust on the Earth, we had volcanism. We had some way of recycling and upcycling very efficiently material from the mantle to bring to the surface. That is really a key process. Otherwise, we would deal only with the elements which you have on the surface, and we have the separation by gravity. So how does that link to widely discussed geological settings? Well, at some of them you see, okay, we have kind of all three phases here. The land, probably formed by volcanic processes. We can have hydrothermal systems, we can have ice systems, we can have porous volcanic materials, we have a variety of minerals, and other scenarios. Most of them directly or indirectly benefit from volcanic processes in form of providing nutrients, surfaces, shelters. So often we were told, like, yeah, but you can't have elements on the surface. What happened to the UV radiation? Well, you just put them in a core, in a rock, in a pore space, and they're sheltered. Works. You can put them in a few meters of water. You can, with this, well, avoid, for instance, being killed by UV. So what is the key, or what is the beauty about all these volcanic environments? I could talk, I think, for 10 minutes about only this slide, so let me drive you quickly through this. We have magma being brought up from the mantle. It might be erupted on the surface explosively, and it might be erupted in something here underwater. What we have here is now various individual environments. They can be hot and pressurized, they can be colder, not pressurized, cold and pressurized. They can have various differences in chemistry. They have different pH. We have gradients driven by chemical composition. We have everything from low pH acidic environments up to neutral and up to alkaline systems. And the most important element in here are the black lines. It tells us that all of these individual environments actually are connected, they can communicate. We have fluid flow through these environments, which means we can exchange elements, nutrients, and that's going to be really, really important for on. What do we deal with? If I mentioned before geomaterials, you might not have heard this often. Usually we say rocks. The key is that there's a difference. So if we talk of solid, we talk of rocks, minerals, and glasses. All of them might have actually the same chemistry. However, their reactivity is crucially and fundamentally different. We can have typical minerals formed by mafic, ultramafic rocks, like magmas like olivines. We have typical mafic rocks, basalt. You see the pores. You see large crystals in there. And you might even see that there are some white speckles in there, which might be minerals again. And we have something which is called glass. Often, if you travel, you hear obsidians, but also mafic and ultramafic magmas can make glasses. These glasses are of peculiar interest because glasses are metastable. So they means they can react easily. Now, before you ask me, do we find glasses in the Archean? The answer is no. And honestly, I'm quite happy about this because it means they're reacted. We can't find them anymore, right? If we would find them, I'm not sure I would be that interested in them. It means they're very, very stable, which doesn't contribute to the reactivity. We want to have reactive agents. And don't worry, the volcanism will continuously reproduce these materials. So we will have kind of on a conveyor belt always new glasses being made, being brought up and done. Last thing I put in here is, next to rocks, we can have them in different sizes. We can have volcanic ash. You see that also here we have quite a variety. They can be dense, they can be porous, they can be glassy, they can have minerals. We work with glasses, and the beauty of the labs I'm working in at LMU is that we actually can produce our volcanic melts and glasses ourselves. So we can take either material like a rock, crush it and melt it, or we can start synthesizing this from the oxides and create a glass with the conditions we want to test. We also can do this under defined conditions. So if you want to have a reducing atmosphere, we can do it. Sometimes this might not be needed, but it's possible to do. And we can reproduce this as often as we want. So, well, I talk about volcanoes and volcanology, so I thought I have to put in some beautiful pictures about volcanoes. Volcanoes are great in shaping the earth. What we have is, we have islands. I focus on islands here. We have Volcano, we have Lipari, we have Stromboli in the back, we have Capilinius on the Azores here, and you see that there's an active landscape formation in here. If you go to Volcano here, you see all these yellowish parts. We have a lot of sulfur, massive sulfur precipitated here, a lot of degassing, continued degassing of CO2 and SO2, mentioned by Thomas, that is really important. So that is one part to shape the Earth effusively without a gigantic, enormous eruption. However, we also have the explosive counterparts. Here you see a nice night photograph of Sakurajima, a lot of ash being ejected. We have lightning in there. How does that shape the Earth? I think you can imagine from this here, all the ash will fall down. Simple principle, what goes up will go down. Unless it's an exoplanet, then it might just vanish. That's something we learned maybe in the morning. So we cover the surrounding with ash. That's going to be crucial later on. What else? If you think of lava flows, you see how lava here is flowing from the wind and it forms different arms. This is a typical type of a lava flow. That might not immediately resemble a lava flow, but it's the interior of a lava flow. What I wanted to point out here at the cross-section, don't try to go in and understand it. The only thing I want you here to do is to appreciate the complexity of the structures. Means this gives us challenges and understanding and opportunities if you look for different environments to place in reactions. So I want to show you a few more, well, examples. I choose basaltic pillow lavas. You might have seen them in some coasts. So these are typical pillows. They form underwater, and these vertical columnar joints are cooling structures. If you look closer, you see in between them here brownish areas. You see them here. If you go over here, you see them even better. These are clay minerals. So is clay erupted? No. If you see between basaltic rock and these clay minerals, you see these dark rinds. This is volcanic glass, actually basaltic glass. This forms when the magma is quenched by water. We form the glass. And outside here, a lot of these is shattered into small pieces. The smaller is the surface, the higher is the reactivity, the excess interaction with fluids. That's why everything in between here is altered to clay minerals. So you already see that we changed mineralogy here. We started with a mafic melt, and now we end up talking about clay minerals. There is many, many more processes. If the images I showed you before were from Etna, now we change to Iceland. This is how such pillow lava flow looks 30,000 years later. You see still a little bit the leftover black parts in here, being the pristine magma, the basalt. Everything else now looks brownish, so it's altered, and we had formation of various types of secondary minerals of clays. You see the complexity we have down here from secondary minerals, fissures. You can go by color. Every color will point you to a different mineral. Again, I just want you to understand the dynamic in here and the complexity we work with. Another crucial element are magmatic hydrothermal environments. So now we're talking of my preferred type of small ponds. Why do I like these subaerial, or at least shallow magmatic environments that much, we have a high variability of fluids, minerals, pH values, temperatures, and all of them, if you look at this one, actually in very close proximity. So this pool to this pool to this pool to this pool to this pool has different conditions in pH, in composition, and in temperature. They are connected. If you go through all of this, you will find that they range in pH from 1 to 9. They go in temperature from ambient to 95. So often I'm asked by chemists, what is the pH I should test? What is the composition? And I think they are not really happy with me because I usually answer, it depends. However, you can see now why it depends, because we have all of these. How should I pick the scenario? We have all of them, and they interact. And there, actually, we have the opportunity to exchange nutrients and result yields from one environment to another environment. On top of that, if we work in ponds, we can have wet-dry cycles, or at least drying cycles. We don't have to go to a complete drying of it. One more thing I wanted to show you now on a micro scale is, again, the high complexity. Thomas asked before about quartz. Well, my question would be, why don't you look at amorphous quartz? So that is what we have here. This is sinters. They form in hydrothermal environments much more easily than we form pristinized quartzes crystallized out. And if we look at silica sinters, we get different pore spaces, we get different areas for compartmentalization, for fluid flow, for trapping, all of that at different degrees, and we can even incorporate water in here. So I think that's something which is really understudied. What do we do in experimental volcanology? We analyze and study volcanic products. So we look at the pore space evolution, permeable pathways, so how easily can gas and water percolate through a rock and through a structure. So here you see an example of this and a simulation of a permeable flow in there. And here you get an idea of the environments we have at the rim of such a small lapillion here. Next thing what we do is we also have to study how does these rocks actually behave if they're put into a hydrothermal system. We do have acidic fluids. They are close to volcanic sites. That's unavoidable. We did this. Now, what I show you is on a study on the Camp Gray. You might see that this rock here is closest to something like a magma. Everything here, none of you, including a lot of my volcanology colleagues, would have said this is a magmatic rock. They're right, they're highly altered. So what you see, if you look at the diagrams below, take the CIA just as an index of alteration. The higher the number, the higher the alteration. We see that we create pore space, we create pathways. So what we have in here, we have a system which is shaping and reshaping, redefining itself. And we add complexity in terms of chemistry, in terms of different mineral phases which we have in here. So the last 5 minutes, I want to show you some specific processes we deal with. Let's start with actually atmosphere and ash-atmosphere interactions. I mentioned I work in experimental volcanology, so I have a lab. We redesigned our standard setup for studying explosive volcanism to fit, well, chemical variability. We can sample this for atmospheres. We can work with subtle overpressure and underpressure. What is the principle in here? We have an autoclave here. There we put ash fragments in. We pressurize this, and then we will open some diaphragms here, and the thing will shoot out into the upper chamber. And a bit what we do is like uncorking a bottle of champagne. You have something in there under pressure, you remove this, boom, explosive eruption. That's what I like to do in my labs if I'm not giving talks or having not a lecture. I can tell you it's quite liberating to destroy rocks from time to time. And having students to do all the tedious work afterwards. So how does it look like? So here you see one of my former students. She finished the PhD now, preparing for the setup. What we do is we film this with a high-speed camera in here. Here, where the action will take place, and next you will see a video zooming in, and you see the ash being ejected, and what you see at the same time is all the lightning discharges happening during the ejection of the ash. So that is something we wanted to put also in the context of the early Earth. So we are first starting to analyze how do we have to start the ideal grain sizes to run the experiments. We tested different atmospheres. This is what you see at the bottom. So we worked here with atmospheres of nitrogen and mixtures of nitrogen and CO2 and carbon monoxide as well, so to have a little bit reducing agents in there. In all of that, we do get frequent lightning activity. We started to analyze the gases and the ash recovered afterward. So far, not the result we wanted to have. We have a few ideas how to implement this, so for this, you have to stay tuned. Another thing we do, and we actually see here, is that's not experimentally done here, but we analyzed ash from this giant eruption 2 years ago at Hunga Tonga Hunga Hapai. It was one of the largest submarine eruption recorded ever. The plume rose actually into the mesosphere, so we had a plume height of 58 kilometers. Intense lightning activities, and the ashes which recovered look like this. So you see this is ash, and we have a lot of salt formation in here. So they bind these together. What does that mean? The ashes interact with the atmosphere and bind salts to the surface, fall back on land and in ponds, and with this you can transport elements from the atmosphere on land and bring them into water cycles. The ashes you find here are from recent conditions, yeah? So don't bring them to the early Earth. Take the concept, please. Another process, looking at high energy lightning, fulgurites, we form fulgurites in there. So this is the work of Zeynep. And with these fulgurites, what you see is you have newly formed crystals, and with this, we managed to actually create an amorphous phosphorus phase, which actually was able to react and be present for synthesis. I want to show you one process for how we can have selective enrichment. So this is done together with a group of Thomas Braun. Dieter Braun, Entschuldigung, Thomas. I'm mixing up people. So here we're talking of basalts, fractures, and we have a system in here where we allow the leaching to be driven by thermophoresis through different cracks in the system. So these heat flows can yield selective enrichment, which is really, really interesting. And that was one of the key elements which we expanded here by the really great work of Thomas Matröm. Here we did this now taking not 3, but a plethora of different compartments. And with this, we were able to actually select and localize, enrich more than 50 relevant substances just by heat fluxes, and we could increase the yield by 5 orders of magnitude. So that is a way how you can get something out of the rock and bring it into relevant concentrations for prebiotic chemistry. We're on the way to do the same for phosphor with phosphorus glasses, so stay tuned here. We have promising results for this. And with this, I want to conclude my talk. I hope I could convince you that we don't have beautiful landscape architects, but we have something which is mixing up the Earth since the early Hadean. We have the mantle-lithosphere exchange, we have the exhaust into the lithosphere of the volcanic gases, forming an atmosphere if the planet holds. And we have a huge amount of different environments which can be linked and work together. And we provide the nutrients needed for a variety of different chemistry. Thank you.